welcome to chapter 8.1, where we talk about random variable and distributions. So in this chapter, we're starting to get into our statistics-based information. And now we have a few variables that you're going to be seeing often that are going to pop up. And based on what the variable is, it's going to have a different way to calculate your probability. So a discrete random means only specific, isolated numbers are going to be classified as discrete. So for example, just the money that is in your bank account, or the roll of a dice, right? The numbers facing up. Those are very, very specific numbers to our daily lives. So for example, if we're talking about roll of a dice, right? We can have 1, 2, 3, 4, 5, 6. Where in this case, we're defining this variable as the number of rolls. So when we go to roll, right, we're going to be looking at something specific happening. So for an example, in your experiment, roll a dice until you get a 6. So your sample space here, all of your different options, and X is going to be determined by the number of rolls you make until a 6 occurs. So for me, I'm going to go on to my dice simulator. There we go. Okay, so I'm going to roll once. Okay, I got a 4, so that's 1 roll. 2 rolls. 3 rolls. Gonna keep going. 5, 6, and 7. So I got a 6 on my 7th roll. So let's see, and I'm just going to do a quick record. So roll 1, I got a 4. Roll 2, I got a 2. Roll 3 was a 5. Roll 4 was a 1. Roll 5, and I'm going to kind of make it up because now I can't quite remember. What did I say? 6 rolls, I got 3, and let's say I rolled 7 times and I finally got a 6, right? I think that was what I had said earlier, right? So for me in this experiment, I had to roll 7 different times and I finally got a 6. So in this case, your X is the number of rolls. So when X is equal to 1, this is 1 roll to get a 6. Let's see, this would have been X is equal to 2. It took 2 rolls to get a 6, and so forth, right? So for me, X is equal to 7. So we got 7 rolls to get a 6, right? So whatever yours is, I would definitely record that, because what we're going to be seeing is we're going to be seeing something like this, where it's the probability of big X, your variable, is equal to little x, your number. So the probability of your rolls, and it took 7 times to get a 6. Now, for some of us, if you had done this experiment at home, which I really encourage you to do, you could have rolled it on your first one or your third one, or you maybe are keep going, right? So with a discrete random variable, it has to terminate at some point, like it stops somewhere along the lines, but it's not set for you. Unlike discrete, right? Finite discrete, meaning it does terminate, but it's a set of number. It's a set number of outcomes. So a racetrack, and maybe this racetrack says, okay, you can't bet more than $100, right? Unlike the last time where we were talking about money in your bank account, no bank is going to cut you off at a certain amount. Hey, you can't have more than $1,000 in your bank account. No, they might have like a minimum for sure, but you definitely have to, this one, you have to end it at some point. So if we're talking about this racetrack bet, we can either have no bets made, $1 being made, $2, all the way to up to 100, and you have to stop no more than 100. So in this case, X would be the amount of the bet. So if we're talking about an experiment with finite, I would like you to roll the dice 15 times and record the number of times a 2 pops up. So again, you have your sample space, and in this case, X is the number of 2s that come up in your 15 rolls. So I would pause the video, do your dice roll, record all of the rolls that you have here. Now I'm going to do one that is pre-recorded. 3, 6, 2. Okay. So in our case, I'm looking for the number of 2s that occur, which I have 1, 2, 3. So in this occurrence, right, X is equal to 3 means that I have 3 2s that are rolled. Whatever you have, maybe you did 1. So this is 1, 2 that was rolled in your 15 attempts. And you can kind of keep going. So again, it's going to be showing something like this, where X is equal to 3, or the probability of X is equal to 3, is that 3 2s have popped up and occurs. So then what's the primary difference that you can see in your experiment? Well, discrete is countable, but it could continue. It took me 7 rolls, but it certainly can take longer than 7, right, to kind of keep going. Whereas finite is still countable. We can still count these values, but it ends after a set amount. So it ends after a set amount. So 15 rolls, 5 rolls, 6 coin tosses, right? It will have to end at some point. Now, if we're talking about now a third variable, this being a continuous random variable, this says that any measure is going to be considered a continuous amount. So usually it's over some interval. For example, the height of an athlete, the temperature of Charleston. So it'll be a variation of values, and it's not so much countable. It's harder to count than these values here, because it can be over a certain range. There's an infinite amount of values that we can have. Now note, we can, X is just a rule. You'll be seeing some interesting rules coming up in some of your homework. So such as the number of tails, or then the number of tails minus heads, or the number of heads squared, that sort of thing. So now we can also do probability distributions with these values as well. So let's say this is some sort of experiment that had been performed. And these right here are going to be your X values. So we can transform this experiment into a probability distribution, where you have -1 that came up, a 0, a 2, and a 5. So when we go to make these probability distributions based on your experiment, right, X, we don't know what X has been defined as. We don't have that context, but these are all the variations or ways to show x. So if this is our experiment, well, how many negative ones came up? Well, -1 came up one time out of 1, 2, 3, 4, 5. So 1/5. So calculating the probability right now is still very similar. We're just now getting into a certain technique. So 0 came up 2 out of 5 times, 2 is 1 out of 5, 5 is 1 out of 5. And keep in mind, if we add all of these together, we should get out a 5/5, which is equal to a 1. Okay, all probabilities have to add up to 1. Now, when we go to talk about your finite random variable, so now experiments that terminate after a set amount. Let's say X is the number of heads that comes up when a coin is tossed 3 times. List the X value list the values for all of X for each possible outcome. What are the possible values of X? Now, we've actually been exposed to this before, but we haven't made a probability distribution like the one you're seeing above for some of these examples. So I would pause the video instead of trying to figure out, okay, well, maybe we can get the first one as heads, 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 and tails, tails, tails. Can you come up with all of your different variations? This is where a decision tree would be best. We have heads and tails, heads, tails, heads, tails, heads, tails. We got heads, 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 tails, heads, tails, heads. All of these different options. Okay, so all of these are your sample spaces. All these different outcomes. So we have heads, 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 tails, and we're just going to continue down the line, getting all of these onto the page. Oh, let's see. Okay. So now that you have all of the different options coming from a 3 coin toss, what we're going to do is now look at what your possible X values are. Now, if you're confused on how we made this one, please go back to chapter 7.2, where we talked about how to make a decision tree. So if X is the number of heads that come up, okay, so how many heads are showing in this first outcome? 1, 2, 3. So we got 3. So this is just going to be X is equal to 3. That's one of your options. Keep moving on. We have 1, 2. So this would be X is equal to 2. And we're going to keep going here. Going to keep going. Heads, heads, heads. And the last one. 1 and 0. Okay. So keep in mind, if X, we're going to define as X is equal to the number of heads showing. Nothing tricky about it, just the number of heads showing. I'm going to move this down here, right? So when we said X is equal to 3, that means 3 heads came up. Now, what are your other variations of X? Right? What are your other X values? We had a 2 and a 2, so that's just a 2, right? A 1, okay, just a 1 and a 0. So all of your different ways to get this X value to happen are values from 0 to 3. So 3 heads came up or no heads came up. Now these are going to be these values that we're going to be plugging in here to your distribution. So we had 3, 2, 1, and 0, or vice versa. You can reverse that as well. It doesn't really matter. A lot of yours actually goes from smallest to largest, so we'll do that here. 0, 1, 2, and 3. So then find the probability of these happening. So I would actually pause the video if these X values are the number of heads shown. Excuse me, the number of heads showing. Then this is going to be the probability of the heads occurring. So 0, right? How did this 0 come about? Well, this 0 was produced by tails, 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 of which there's only how many different ways to get here? There's only one way to get a 0. So that is 1 out of 8 total options. 1, 2, 3, 4, 5, 6, 7, 8. How many different ways can a 1 happen? Well, that was by heads, tails, 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 heads, tails, and tails, tails, heads, right? Actually, I'm going to rewrite that to make it look just a little better. You said that was okay, so that was 3 out of 8 different ways to calculate it. Okay, let's do it again. For 2, we had heads, heads, tails, heads, tails, heads, and tails, heads, heads, which there were 3 out of 8 different ways. In this last one, only heads, 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 so 1 out of 8. Again, adding up all of your probabilities, we should get 8 out of 8. I'm going to just redo this one ever so slightly. This was tails 3 times. Let me move this over. Just making it look a little better for when I go to print off some of these guided notes. All right, you made your probability distribution, and now we can answer a few questions. We want to know, well, what is the probability that X is less than 2? Well, the probability that X is less than 2 means the probability of getting less than 2 heads, right? Which means you can either get a 0 heads or a 1 head. So we can add those probabilities up just like we did back in chapter 7.3, where we said this is really equal to 3 out of 8 plus 1 out of 8, which is 4 out of 8 or 1/2. Let's try it again one more time. Let's do the probability of, let's see, let's do something like 1 less than or equal to, no, we'll do something like 0 less than or equal to X less than or equal to 2. Right, so maybe it's a range. Again, this being a range of these values. 1 out of 8, or probability that X is equal to 0, so that's part of it, right? Plus the probability that X is equal to 1, plus the probability that X is equal to 2. That's what it means to say when X is greater than or equal to 0 or less than or equal to 2, or X falls in between 0 and 2 inclusive. Inclusive being that little equal sign underneath. So that's 1 out of 8 plus 3 out of 8 plus another 3 out of 8 to make 7 out of 8, right? 1 plus 6 is 7. So you can do a whole list of other options depending on your distribution. I'm just going to move this quickly down. give it just a little bit more room, right? So you can have a different range. You can just be asked something simple like the probability that x is equal to 1, that being just 3/8. Now let's try, let's keep going just a little bit more. So let's do it again. Actually, it's okay. It says that if x is a finite random variable with n1 and n sub 2 values, then its probability distribution, just what we did just a moment ago, lists the probabilities of these values. So when x is equal to 0, we found its probability. However, when we finish, we will always want to make sure that the sum is always totaling to 1. So now if we have the probability that x is equal to little x, means we're looking for the probability that a randomly selected variable x has a specific value, this being little x. So big X is your random variable being selected, and this little x here is just your specific value. Okay. We're going to skip the next part. I don't know why I keep forgetting to take these off. I just think we have better examples to show you guys rather than something that's so simple. So probably like this one. So I would pause the video, see if we can answer the following question. It says, the following table shows per capita emissions of greenhouse gases for the 30 countries with the highest per capita carbon dioxide emissions. Emissions are rounded to the nearest 5 metric tons. Consider the experiment in which a country is selected at random from the list. Let X be the per capita carbon dioxide emissions for that country. Find the probability distribution of X. Use the probability distribution to compute when P of X is greater than or equal to 20 and interpret the results. So we are going to be asked to create a probability distribution and then ask the following questions. So this is a great place to pause the video in case you are trying to get started. For your X values, because we're going up by 5 metric tons, we're going to be starting at 0, then 5, then 10, then 15. And if there are any values that don't fit in that mix, we're just going to be entering in a 0. So 20, 25. Okay. So based on your chart, see if you can figure out these X values and their frequencies. So on our table, no country has 0, which means your probability is 0 out of, how many countries did they tell us we had? Well, we have 30 countries. And again, same thing for 5, 0 out of 30. Now 10, we're going to count how many 10s we have. In our case, here we have 13 10s. 13 out of 30. 15 kind of has a little bit of an overlap. I'll just keep going with this. Maybe I'll alternate colors. Green, we'll just do green. 15, 20, 25, 30, 35, and 45. Okay, so we're just filling out the chart based on the information that has been provided to us. You have 7 countries that are in the 15 range. You have 5 that are in the 20 range. 25 is 2. No, oh my goodness, I'm just writing the number underneath. 30, 30, 30, 1 out of 30, 1 out of 30. And if you want to reduce your fractions, you certainly can. 1 out of 15, 1 out of 6. I think that's all that reduces. Correct. So if this is your probability distribution, right? You've calculated it, you did all that hard work. Now let's figure out the probability when x is greater than or equal to 20. Well, what are the values that are greater than or equal to 20, right? Well, x values that are greater than or equal to 20 are spanning right here. So if you wanted to, you already did the hard work with calculating the probability. So we can just add the probability starting with 20 when x is equal to 20, plus the probability when x is equal to 25, plus, and you go all the way up until you hit the last value of 45, right? And those probabilities. So 1 out of 6 plus 1 out of 15 plus so forth, 1 out of 30, right? That's a really long process. You can add all of them up if you'd like. Or what might be a little easier is to negate that fact. Notice that there's only 3, actually, well, there's 4 in total. There's only 3 that have meaning that we can just subtract out. So we can say, well, we could do 1 minus the probability that those who emit 10 plus the probability that those who emit 15 metric tons. So 1 minus, what is that? 13 over 30 plus, let's see, 7 out of 30. And then that would be your answer. So I'll show you that quickly. We can do that on Desmos. It's a 1 minus. Then we have 1 out of, nope, we have 7 out of 30. Let's see, delete 7 out of 30. Plus, notice that I'm doing parentheses so that I can add, plus 13 out of 30, close parentheses. So about 1/3 or 0.333%. Otherwise, you can certainly add up all of those probabilities. We had 1 out of 6 plus 1 out of 15 plus, notice how it's going to take me a minute, 1 out of 30 plus 1 out of 30 plus, let's see, one more, I think, 1 out of 30. And there you go. So you can do one of 2 things. Please don't be afraid to negate some of these facts and put it in there. Uh, 1/3 or about 0.33. Now, if you were to do this graphically as well, so if they had you make this chart, make sure you're able to bring the context to your chart. You can do that by having these all in terms of 30 on the bottom, and then making what we do in Excel, right? We choose the graphs in Excel, be able to put this into a graph visually. Now, you don't have to do it by hand for me. The ones on your homework and on your tests and quizzes, they have already been completed for you. You just have to be able to read it. So if we were to make some sort of a quick chart, right? For 0 and 5, we're down here at 0, and then you go up to 13, and then you go down to 7, maybe somewhere down here. Then you go down to 5, and then to 2, and then to 1, 1, 0, and then back to 1, right? So be able to read or place this on a chart accurately. And what I just did was just the frequency, but their probabilities should follow suit as well, having things being pretty equivalent.